Thanks for visiting my talk. My name is Dave, and I will present you affordable EMFI attacks today. It's also an introductory talk into EMFI a bit, and it's supposed to help you get started even if you're new to this topic, and compared to other talks you get like the 0 to 100 into EMFI, especially on a budget. First I will start with the motivation for this. Why even do all this trouble? Then I will introduce fault injection and EMFI to you. And then the main part will be the setup, how to build it and how to run it in an affordable manner. And in the end I will show that the setup works and on actual recent and relevant targets. So nowadays we have modern security features in many chips, even the very cheapest chips. And the question is, does it make classic attacks obsolete? What I mean with this are like connecting a JTAG debugger, or simply reading out the memory that way, or just replacing the ROM, modifying the memory. And indeed, like we have nowadays closed debug ports, we have secure boot, we have flash encryption, which can make the attacks more difficult, but not obsolete. It's just an extra layer to get through until you can then do the same methods you would do before. Yes. So how to bypass these methods? That's fault injection for you. So you can do different types of fault injection, which then allow you to skip an instruction, like a check for a secure boot. You can have fuses, and you have to read those, right? And then when you have the result from the read out fuses, you can just ignore the result. Yeah, the field is relatively new, so many devices have no countermeasures against EMFI or other types of fault injection. And the whole setup is not really something you find in one place, open source, really available and accessible. Some tools are very expensive, other tools are accessible, but then you have to add some custom components always to make it a whole system, right? So my idea was to make a reproducible system for everyone to build. First of all, let's take a step back. What is EMFI or fault injection? As I said before, in fault injection you introduce a fault into a system. You might remember if you have like these ideas of safety in aerospace, or in general you have solar rays which can affect systems. And these are faults, right? And we want to try to do this in a controlled manner to get the outcome that we want. A very specific outcome in usual cases. And of course you have the software fault injection, like Rowhammer and this type of stuff, where you exploit the hardware and you induce hardware faults through some software tricks. And you have physical fault injection, which is what we're doing here. This means that your code can be super secure, it can be perfectly written, you can have all the checks in the world, you can have fuses, you can have whatever you want. When you get the chip in the lab and you modify it from the outside, there's not much you can do about it. EMFI in particular leverages electromagnetic pulses that are placed exactly on top of an SoC. And I think I'm the first one who is quoting a 19th century textbook at this conference. But the principle is like, just to say, it's like not that special. It's you have Faraday's laws, and you have magnetic fields, and magnetic fields that move across each other and use currents. And if we do this very localized, we can affect very specific areas of the chip and very specific instructions or memory regions or registers even. Yeah, by affecting the transistor behavior, like flipping a bit or skipping in instructions, you modify the program flow, even though the code is actually secure. Yes. So in the picture, again, it's like just a modern version of the experiment on the left. Where you have on the left you have a battery connected to a coil, which forms an electromagnet. And then, according to the right-hand rule, it forms a magnetic field in the z direction. And you move this electromagnetic field through another coil, and then it induces enough current to power a lamp. So there are possibilities for mitigations, but they typically require a hardware revision change. You need a new component or a new board at least. The upside for vendors, I guess, is that the impact is limited, since you do need hardware access to the device. And but for us it's well suited, because we're trying to do firmware research very often, and if it's all locked down and we don't have the firmware, this can help us to bypass checks and dump it. Here's just one more example with some pseudocode. Usually, of course, we look at assembly, but let's say we have a static variable or a static bit or something like this, which is set to false. When it's red, we can fault it, and maybe it returns true. Or when it's checked here, either the evaluation of the statement, if debug enable is true, it wants to go into a branch instructions and we skip the branch instruction. Or also we could modify the static variable in memory. For EMFI both you need good timing and good location. You need the right instruction, of course, so you need the right delay from a certain known signal, like a boot time. And also you need to find the affected SoC area, which you can fault. Just so you have a picture about the time scale we're talking about, by using an FPGA for timing, we have 400 MHz clock, so it's a 2.5 nanosecond step size. This is fine for many targets, and if you're faster, you might need faster clock or more tries. To discover the timing for the fault, you need either to look at the code or binary, reverse engineer the binary. You can also use power traces and see where the code is happening that you want to glitch, or when it is happening. Here you can also see that an example where we have a reset line, we take that as an input. Then we have the delay that we have to figure out, of course. When the delay has passed, we trigger the EMFI device. And we need to be able to really time this very accurately to get reproducibility, and also the pulse width is also something you want to fine tune. The setup consists of these devices. It's really not that much if you think about it. You can position your EMFI pulsar by hand, but you really want to do it methodically probably. And the positioning platform, as I will show later, can be quite cheap, so I don't see a reason not to use one. Then you want to generate the right delay, which you can see the FPGA here. Then you have different choices of EMFI pulsars, which are triggered by the delay generator, and the device under test, which should give the delay generator the input to create the timing. The timing could also be from a device like firmware USB. So if you trigger on a USB packet, that could also be a trigger. Or different types of triggers exist, but for simplicity, I'm saying that the device under test triggers the delay generator. And as you can see on the right, you should make a map of your chip, and especially for sanity checking, if you have some specific effects, they usually occur in an area and it should be grouped a bit. Here's how it looks like in real life, everything assembled. So for positioning, we use the CNC and the other components I showed before. Here's a close-up. So you don't need that big of a positioning platform because, of course, it only has to have as much X and Y travel as the size of the chip. And you want to mount it securely, then you can start. For the positioning platform, you have a few options. CNCs or 3D printers are very good idea because they are like made in mass production and they're quite cheap. They are also used interchangeably since they all use G-code. So everyone who's worked with 3D printers knows this. They come with the motor controllers, with the motors, with the end stops, with everything you need. One thing I would like to mention is that lead screws have 10 times more backlash than belts. So if you have the choice, I would probably recommend a 3D printer, or what you see on the right is a drawing robot, which is probably even better for you because you don't need to buy the spindle or the printhead because it's just the positioning to put the pencil in it. So backlash, just in addition, it means if you move the position, move away, move back to it, it won't be perfectly accurate, right? And if you have less backlash, that will be more accurate. On the bottom, you see a motorized XY stage, which is used for microscope and such. And those are much more expensive, and in my experience, they offer small benefit for the price. And on these IoT targets, really the CNC was definitely enough. Next up is your delay generator. I'm using the chip.fail bitstream by Stack Smashing. It's open source on GitHub, and it works on the very cheapest Vigilant FPGA, the CMOD A7. It costs €100 or dollars. And what I like about it is that in theory, it was made for voltage glitching. So you see on the right of this orange dot, it's actually his PMOD adapter for voltage glitching. But just by changing this component, we can do EMFI as well. By using the screen board, which I'm calling EMFI Companion, you can do the EMFI as well with the same setup in the team. It also has a Python library and API, so that's awesome. You could also even use a Raspberry Pi Pico if you're fine with a more coarse timescale. It's still like work in progress, but I've had some good results with it as well, and of course it costs even less, about €5. I guess you can also overclock the Pico, so that's also something to look into. Lastly, you can use a chip whisperer. We have the very latest version here on the picture. It costs though about €500 instead, so I think the FPGA is the best and most versatile option. For inducing the pulse, I think you have three options again. Either you use the chip shouter, which I show in the top. It's more on the expensive side, but it's nice and safe. It's in a metal case. You could use the Pico EMFI, which is open source again and much more affordable. Although I like that the chip shouter goes to a higher voltage. If you have higher voltage, you can make shorter pulses, since lower voltage doesn't discharge as fast. And lastly, we have a silicon toaster on the picture, which was developed by Ledger, and I know they always use this in their presentations and in their attacks. But unfortunately, it's not open source. I mean, there's a paper, and I guess you could build it yourself relatively easily, but it's not just pulling the sources from GitHub and sending it to a fab. The good thing about this one is that it goes to 750 volts, so if you need that, maybe look into that, or maybe modify the Pico EMFI, I guess. I added a few custom things to the setup as well, which will be available online too. First of all, I made a hardware reset. This is a nice PCB version of what I built earlier. It allows you to power the target to a good power supply, not like to a USB, but for instance to a good linear lap and power supply, or to a barrel jack if that's what you have, or even USB also. And with just a single GPIO from a FPGA or microcontroller, you can turn it on and off. And it's like a very stupid thing, but I was looking online, I couldn't find anything ready to go. Everybody told me, yeah, I use breadboard with the transistor. And I didn't like this because the components always fly out and you lose your wires and you use the whole day because the jumper wire flew out of the breadboard and stuff like that. So I guess it will be convenient for different applications as well. I'm using a assembly connector for everything. This was motivated by Colin of Linz devices, which also use the same cables. And again, the FPGA breakout. I will show later what I'm using or what I used up until now, which is basically a combination of the two, but this will be more modular. And this is also just a trigger input and the glitch output, and then the delay is done by the FPGA. Also, you have the reset output that would be perfectly suited to go into the hardware reset. As well as debug LEDs, debug pins for everything, so you can customize that to your liking, but by modifying the bit stream as well, right? Then the software is, for one, is EMFI control, which I called it, where you can move around your device, you can move around in a controlled manner, you can probe different things, you can list your devices, and you can script this. And this then I used in my fault campaign script, where I imported, and it's easier to work with that way. As well as the fault campaign script will write it all to a CSV, and then you can pass the CSV and visualize your results. As I mentioned before, you really want to do a map, a 2D map, so you can see whether you have some outliers or you have some grouped faults. On this target, we have interestingly, it was more sensitive to crashes and brownouts in the exact area where I also was able to get the glitches. It kind of makes sense. Yes, as you can see, a whole area is affected, right? So basically, the backlash and the accuracy of the CNC isn't a problem because all those yellow dots are all fine. Like all of those work to skip instructions, but I will explain later. Here's again the power, the hardware reset, and the glitching breakout 2-in-1, let's say, with a bigger FPGA, but you don't need that one. And in the back, I have my old hardware reset. Like it's messy, so I'm happy to have the new devices. I tested the setup on a quite modern chip, which you might all know. It's supposed to be protected against voltage fault injection, and there were many results on predecessors of this chip. They wanted to fix voltage fault injection, they wanted to fix side channels, but apparently EMFI still works. It also has secure boot and different other features that should all be attackable through the same method. But first of all, I will explain how to characterize a chip for faults when you have it. You want to get a test board, a development board, program it with your custom firmware, like a simple loop as shown here. You pull a GPIO pin high, then you do 100 additions, 1,000 additions, the same assembly instructions over and over again, and then you can pull it low again and check the result. By placing the glitch in the middle, it should modify the result, right? If it's successful, if it's susceptible to glitching, then the result should change. There were a few challenges maybe to keep in mind. I did use the default toolchain, so I get the free RTOS and all the protections. because I want to be as close to the real world deployed devices as possible. So it has brownout detection, for instance. These are not dedicated fault injection countermeasures, but they are safety countermeasures that make sure if your battery voltage drops or something in this regard, your device will be reset instead of starting to do wrong computations. But of course it makes the glitching a little bit harder. Then such loops, as I described earlier, was just optimized away immediately. So you want to probably do inline assembly. And lastly, what also was funny, this chip has embedded UART to USB. And since USB is a mess, I mean, the A is already asynchronous, but if you send now, it sends now. If you do USB, you never know when it sends, and it's falling all the time. And as we can see here, I have my GPI open high on the top. Then I have my, on the bottom line, I have the glitch pulse. It's narrow, but I hope you can see it. And the USB packets are just in the middle, like fully out of place, and it was corrupting my communication. Yeah, many pitfalls. But in the end, we got the instruction skip, more than one actually. It looks like the CPU or compute area of the SoC is in the top left. I would like to look into the chip, into the die shots as well, but they don't exist yet. And that would help to identify where's my memory, where's my RAM, and where's my CPU. It's just one CPU on this chip. Yeah, and also in another test, which I don't have a picture here, you can see that the whole left top corner is protected by brownout detection, so it was giving me brownouts all the time with the wrong parameters. And with the fine-tuned parameters, I was getting this nice yellow area. You also see the CSV visualized, where it's returning no, nothing happened, 100 in most cases. And then when it would glitch, you would get the 99, 98, 97, something like that, where you would see that it skipped a few instructions. Also sometimes boot logs, right, when it would reset. There were also clock-related crashes in the center right area, which was funny, because again I was getting boot log all the time, and I could see why it crashes. So maybe there's an oscillator or something in that area. And again, die shots would help. This is just an example of a different chip where you can see how RAM areas or memory areas look very different from computing areas. And yeah, as of about the impact, I'm quoting limited results from 3 years ago. He said there is no way to fix, but you can buy the new chip. And I don't think I could put it any better. I mean, yeah, it's generally an advanced attack. So right now, it's not something you can do quickly in the field. So if you have some devices deployed somewhere, it might be simply outside of your attacker model that someone goes there, grabs it. You don't notice that he puts it in a lab. It's gone for days. You don't notice that either. Then he puts it back. You don't notice that. You know, that's the question if it's in your attacker model. But you should be aware that it is possible to skip security features, skip code paths, even if your code is perfectly fine. You might want to look into other chips if you know that your chip is vulnerable. The other chips may be more secure against it. Maybe different architectures would be better, maybe faster, maybe more cores. It just makes it a bit harder to get it done. Yeah, as a conclusion, it's a very low cost, mostly free open source software and hardware. You need the XY stage for, I guess, about $200. You need the EMFI processor, it might cost about $2,000, but you can, again, use a Pico EMP. And you need the delay generator for about €100, and the small PCBs and extras, it's not much, right? So I hope it's easy to see that it's not that high of a hurdle or entry barrier. And it can even be improved with little extra cost, if at all, like using a 3D printer or something belt-driven instead of a CNC. Use a proper hardware reset that doesn't that is reliable. You don't want it to reset your target when it shouldn't. And maybe you might need a higher voltage pulse. I spoke about the PQMP. I haven't tried it on this target, but it doesn't go as high with the voltage. And I did need the almost 500 volts from the chip shorter on this target. If you don't get the results you expect, maybe try higher voltages or a device that goes to higher voltages. And lastly, your device can be secure against voltage fault injection, against side channels, but like a serious attacker, like shown in the picture, of course, we know they always look like this, will always find a way. And I guess this is also an invitation to always try to find a way and also always keep hacking. I have quite some time left, so I'm open for questions, and thanks for listening. Yes. Yeah, sure. So the question was about how to find the right delay. Basically, the delay you want is, of course, first and foremost based on when you or which instruction or which feature you want to skip or glitch. And sometimes you can get like source, let's say, of the application or the bootloader or whatever you want to glitch, and you can modify it to add some GPIOs or hints like that right before the important instructions, and you can time that with a scope. You can also check out the power signature or EM side channels. For instance, if you are waiting for some crypto operation to happen on boot, you can see when it happens and on your scope, and you can use that as a reference, and then you want to just go a bit earlier and then sweep a little bit in the time domain. Yeah. Yes, in the front. Yes. How did you know? In a previous talk, previous chips from this chip family were successfully glitched with different methods, and they said that the manufacturer told them that new versions will be protected. So I thought, let's look at the new versions. Yeah. Okay. Thank you. Yes, in the back.
At what stage of the boot up sequence are you able to compile and run it, or does it make a difference if you run it in the application layer and identify a region? Does it necessarily apply to the secure boot, let's say, skipping the security measures?
So since I was doing like a constructed example, the timing wasn't that essential, and I was mainly looking for the area and then whether it's susceptible at all to this attack. So for applying this knowledge to a secure boot, for instance, which you mentioned, you would have to also find the timing, but the area should be mostly the same, I guess. This chip does have crypto accelerators and crypto features, and I guess those might be in different areas of the SoC. Although in the end, your application code has to check the result, like what comes back, it has to check that. And that might be in the same area again. So, yeah.
Okay. Do we have any other questions? No? No, thank you, Dave. Okay.
I can tell you later. I can say about the disclosure and stuff. I give the manufacturer a lot of information, but I didn't get the full okay, we identified and reproduced it, so therefore I'm not 100% saying which model. Yeah.
Thank you.
Thank you very much.